Now, if we look at the actual distribution of asset prices and or more particularly returns, and the question is, how well do they fit the normal distribution? Here's the S&P daily data and weekly data for I forget the period of time quoted in the book, but it's just a sampling of data from the S&P 500 price series on a daily and a weekly basis. And what you tend to see, and this is very common in financial data, and that is that one often sees in financial data that the observed probabilities compared to the normal assumption have two characteristic properties. One is the probabilities of events close to the mean are too high, and these are high, I'll call it plus, and the probability of extreme events in the real world are also too high. And then you see that the probability of intermediate returns tends to be too low. And this is a common profile of real-world financial data versus a normal distribution. And that is that in the real world, returns tend to be too often close to the mean and too often very far from the mean compared to what the normal would assume, and too seldom in this intermediate range. You see this gap where the actual observed probabilities are below what the normal distribution would require. But you see fat tails is the common terminology one finds in the financial markets, that financial data tends to have fat tails. Probabilities of extreme events are higher than the normal allows, but also you always have these peaks in the real world data, namely that the probabilities of very small moves tend to be greater than the normal allows. And you'll see the same profile in this data for IBM. Again, here it's a little less obvious in the daily data. If you had numerical values, you would see the fat tails. You can't quite see them here because of the resolution of the graph. But you see it a little more clearly in the weekly data. You see the fat tails. The real-world data is sticking out there. You see always this central tendency, and then you see the gaps in the middle, somewhere between 1 and 2 standard deviations. Things don't happen very often. Another way of observing normality or lack of normality is to look at these so-called normal probability plots. And these normal probability plots tend to be done either in terms of the z-values, where you look at the normal z-values, and so a z-value of +1 is 1 standard deviation. The z-value of -1 is -1. So we can do it in terms of z-values or in terms of the associated probabilities. And then what one can do is to graph what would the normal distribution of data. So if I had data with a given mean and a given variance, what would the normal distribution with that mean and variance, how would that plot? And usually that's represented in a dotted line in the graph. And it might be the same with the z-values. With the probability plot, it's a little bit neater, because then we would expect a straight line in the normal distribution. And what one can see is in the probability plot, you have the couple of points in this example don't quite line up with our normal probability. And in a situation like this, it's hard to know what this means. It could well be that the data are not normally distributed, or it could just simply be you have so few data points that you can't quite tell. If you generated 6 random sample from a normal distribution, it again wouldn't perfectly line up with the theoretical plot either. But you can, in fact, look at data in with richer data sets, and you would see profiles. Well, first of all, let's look at a couple of normal profiles. So this is what things would look like if we generated 1,000 data points from a normally distributed random variable, had a mean of 3 and a variance of 25. So you see the mean is right here. It's also the median. The mean and is going to be the 50th percentile. So there's the mean. And you can see that these theoretically generated points do lie right on the line. There's going to be a little bit of discrepancy. There's going to be some sampling error. And if you could imagine just picking 5 of these points, calculating the sample mean and the variance, and they might look quite different from the normal plot with that sample mean and variance. And that's in part the problem I was pointing out in this earlier plot. You can't quite tell because there's not enough data. But if in this plot where we have a lot of data, you see that the generated sample data really does fit the theoretical distribution quite well. So now the question becomes, what would happen if we had 1,000 data points, for example, of daily price data? You get about 250 price points per year, about 250 trading days a year. And so if I had 1,000 data points, it might be 4 years of daily data. That's how you might think of this. 1,000 points, 4 years of daily price data. What would they look like? And in fact, what they would look like is they wouldn't fit the normal probability plot very well. We would see some of the same tendency. You would have the theoretical normal, this would be the normal, of the same mean and variance. So the plotted line, the dotted line, of course, reflects the mean and the variance of the sample data. So that's the theoretical distribution that we are hypothesizing the data might satisfy. And the profile that you see of the raw data, and I'll just put it this way, will almost always tend to look like this. Fits pretty good in the middle. And it fits pretty well in the middle. There's a little bit of deviation because of the point I made that the actual data tends to have not enough probability mass between 1 and 2 standard deviations, say, too much in the middle. But that averages out by the time you get here. But notice the tails, how the fat tails look. Now, why is this evidence of fat tails? You see that the real data, which is the squiggle line, the real data is above the normal probability plot for low z values, and it's below it for high. Well, here's the reason. Let's take an example. Let's take a look at this point right here. In the real world data, let's say these are probabilities. In the real world data, that point is corresponding to a certain percentile. Let's imagine, for the sake of argument, that z value is corresponding to a 10th percentile. So here's the z value. And so I guess I should call the 10th percentile here, and I should call this 0.10 as a probability. So I have this point with the arrow on it. It's a point from the actual data. And according to where it plotted in the real data, it's at the 10th percentile of the raw data. 10% of the data is lower than it, 90% is higher. Now if I look in the normal probability plot, where is Z10 in the normal? Well, Z10 in the normal might have a probability that's much, much lower. That's what it's telling me. Might be 0.2. So that's what gives it a fat tail. That point in the raw data has 10% probability mass to the left of it. In the normal distribution, that point would only have, say, 2%. So that's why the real world data has a fat left tail. You have the same argument on the right. I have a z point here, say Z90, I go up here, that in the real world data, that corresponds to 90, but on the normal plot, that z value might be a much higher value. So you have a fat right tail. Okay, and so this profile of the raw data being above the normal probability plot on the left and below on the right is evidence of these fat tails.